Okay, so we break down the motion of this parachutist into different sections of motion. So the first part, all right, for this is a Cambridge question, all right, O-level question. What I'm going to do is I'm going to modify it slightly because this question doesn't show the first part, which is constant acceleration. All right, so I'm going to add one more section there. Okay, I'm going to add one more section here. I'll call it A prime. Okay, I'm going to call it A prime. So you have A to A prime, and then A prime to B, then B to C, then C to D, D to E, and E to F. Okay, so I'm going to explain each part one at a time. The first part is from A to A prime. All right, now what's happening from A to A prime? Now this is the part where sometimes Cambridge will not draw the straight part. They will just straight away go to the curved part. All right, but I want to break it down to as many parts as possible. Okay, so if at the beginning of the parachutist's fall, he will be falling at constant acceleration because air resistance at that point is negligible. Okay, just like any object that's falling under gravity, let's say you drop your eraser from your table to the ground, it will not experience much air resistance at the beginning. Okay, but if you drop it from a plane, then eventually the air resistance will be significant enough for it to reach terminal velocity. All right, but when you drop it from a table, it's not going to reach terminal velocity for sure. All right, so that's why the first part is actually constant acceleration. Can someone tell me what this acceleration is? Yes, 10 meters per second squared, or 9.81 to be more specific. Right, the value of acceleration initially is equal to g. Okay, now let me draw the diagram. So at this point of time, there's only the weight. Okay, W stands for weight. All right, I'm just going to write it for the first time. Okay, for W is weight. There's only weight acting on the object. There's no air resistance yet. Air resistance is negligible when he first starts falling. All right. So the force, the resultant force, F net, is equal to the weight, right? So the person is falling with constant acceleration. Acceleration, which is equal to acceleration due to gravity, right? For us, we'll use 10 meters per second squared, or 9.81 meters per second squared. Right, so that's the first part of the motion. Any questions? Okay, so from A to A prime. All right, next. Okay, from A prime to B. Okay, what's happening? Which force is present now? Air resistance, yes. So what's happening to the air resistance? Is it increasing, decreasing, or constant? Okay, good. It's increasing. So I'm going to call it R. Okay, air resistance. I'm going to call it R. Okay. Now I should draw the line for W a bit longer. My apologies. The line for W should be longer. So what's happening is that air resistance is increasing. Okay, air resistance is increasing. So when air resistance increases, what happens to the resultant force? Good. It decreases, right? Because the resultant force is the weight minus air resistance. So when the air resistance increases, all right, the resultant force will decrease. Okay? So you think of W minus increasing number, right? W minus an increasing number, therefore the overall number will drop, become smaller. So the resultant force decreases when the air resistance increases. Are you all following? Okay? So now if we use Newton's second law, right? If the resultant force is decreasing, what will happen to the acceleration? Decreases as well. Because F equal ma, m is a constant, So when F net decreases, A also decreases. Do you follow? Okay? So the motion now, right, is decreasing acceleration. Do you follow? Decreasing acceleration, you can see it from this graph here. It's a curve, right? The gradient of a speed time graph is acceleration. So when acceleration decreases, right? When acceleration decreases, that means the gradient is decreasing. So the curve, the speed time graph, right, will show a curve like this. Okay? Any questions so far? Okay, next. From B to C, all right? What's happening from B to C? Can anyone guess what's happening from B to C? Sorry? Constant speed, very good. Now what's happening? Why is there constant speed? Very good. The air resistance is now equal to the weight, all right? The air resistance is now equal to the weight, all right? So what happens to the resultant force? What's the resultant force? Anyone? 0, yes, very good. All right, it will be 0, okay? Resultant force will be 0, and when resultant force is 0, that means that it will be traveling at what? Constant speed or 0 acceleration, okay? So the motion here will be, there will be 0 acceleration, and therefore constant speed. All right? This constant speed is known as the terminal velocity or terminal speed. All right? Okay, if we take direction into account, then it's terminal velocity. All right? Okay? Any question? So if you contrast this to the beginning, all right? When it is from A prime, there's only weight present, so the resultant force is equal to ma, right? Okay, where W equal to mg, the acceleration is actually equal to the g, okay? Acceleration due to gravity, right, at the beginning. Okay, that was part 1. So over here now, the forces are equal, right? Upward force equal downward force, resultant force is 0, therefore it's traveling at constant speed, no acceleration. Is that okay? Okay, next. Okay, over here, the parachute opens. At C, the parachute opens. Okay? At C, the parachute opens. What happens to the forces now? Can anyone tell me? Air resistance, is it more or less than the weight? Air resistance is now more than the weight. All right? Air resistance is more than the weight. So if you talk about the resultant force, F net will be equal to W minus R, okay? And since R is larger than the weight, all right? What will happen to the resultant force? It will be negative, okay? Maybe I shouldn't use the arrow up because that means it's increasing. I should just say that it's larger, okay? Right, so now, since the resistance is larger than the weight, right? R is more than the weight, therefore it will be negative. The resultant force is negative, and since it's negative, F net equal to ma will be negative. Okay? So since the resultant force is negative, the acceleration will be negative. All right? So the motion of the object, okay, is going to be negative acceleration or deceleration, okay? All right, but is it constant deceleration? Okay, we need to look at the graph, right? If it's a straight line down, it's a straight line downwards, then it is constant deceleration. Okay, so we can use the word constant for that part that is straight, a straight line. All right. Okay. I'm adding this part post-production to ensure completeness of the explanation. Now the new part that I'm adding is C prime, which is between C and D. Now at C, we were saying that the parachute opens. When the parachute opens, after that, the air resistance is more than the weight. All right, so when air resistance is more than the weight, it cannot suddenly end at D, where the air resistance is equal to the weight. So at some point, the air resistance must start to decrease until it's equal to weight. And that is actually between C prime and D over here. From C to C prime, we were saying that when the parachute opens at C, after that, R is greater than W. Air resistance is greater than the weight. So between C prime to D, let's take a look at the graph. Between C prime to D, right, there's a curve there. That's the part where the air resistance now decreases until it's equal to the weight. So initially, R was greater than the weight. So I draw a longer arrow here, right? This is at part C to C prime, right? And after a while, air resistance decreases until the air resistance is now equal to the weight, right? So that is the point D. Now we go on to the next part, which is from D to E. Now, as we saw the video just now, right, eventually the parachutist will reach another constant speed, right, which is now much slower than before. Okay, now it will be much slower than before. It's from D to E, right? CD. Okay, I should put CD over here, all right? So the CD over here, and then here is DE. All right, so here it reaches another terminal velocity. All right, the speed is constant now again. So here it is similar to earlier on where the weight is equal to the air resistance. Right, weight is equal to air resistance. Therefore, resultant force is again how much? 0. All right. Therefore, the motion is again, okay, since F net equal to 0, therefore there is 0 acceleration and constant. I'm using the word speed throughout this question because the graph given is speed time graph. If it's velocity time graph, I will use the word velocity. Okay? All right? So it's going to be 0 acceleration, constant speed, but at a lower constant speed than earlier. Okay, it's going to be much lower. This is the speed where the parachutist will hit the ground. So it cannot be very fast. Okay, even though, but it's still dangerous, okay, if you're not careful. If you all remember a few years ago during NDP, the parachutist was supposed to land on the platform, all right, and there was a horizontal draft causing him to flip, and then he injured himself, right? Given that he's jumped thousands of times, okay, that shouldn't happen, but it's because of the unpredictable horizontal wind, so it's still quite dangerous, okay? So I think after that, they stopped the practice of landing on the platform. Okay? So it's a much lower speed now, much slower constant speed, right? But it's still dangerous lah. Okay, so eventually the parachutist hits the ground, and that is EF. Do you see that it's not a vertical line? What does it mean? What's this EF? What's happening? Yes. So the parachutist hits the ground. Okay, and the motion is constant deceleration. Okay, it's a very high deceleration because he stops in a very short time, less than 1 second, right? Within 1 second, he stops. So the line is very steep. It's a very steep line, so the deceleration is very high. Okay, so which is why it's very important for them to land correctly. Okay, now let's think about Newton's laws now. Okay, from section A to section 6, section 1 to section 6, can you tell me which Newton's law do we use? Okay, which Newton's law do we use? I'm going to use another color. All right, from A to A prime. What Newton's law do we use? Remember, in general, when there are balanced forces, we use Newton's first law. When there are unbalanced forces, we use Newton's second law. Okay? In general. Okay? So the first part, A to A prime, is it balanced or unbalanced forces? Hello, class. A to A prime, the first section, is it balanced or unbalanced forces? Okay, good. So Newton's second law. Newton's second law. All right? Because there is resultant force here. There is resultant force, therefore there is acceleration, right? Okay, from A prime to B prime, it's the same actually. There's still unbalanced forces, right? Still unbalanced forces, so we use Newton's second law, F equal ma, right? F equal ma. And then over here, for BC, do we use Newton's first law or second law? Very good, Newton's first law. Okay, why are we using Newton's first law? Yes, balanced forces, resultant force is zero. Resultant force is not balanced, resultant force is zero. Okay, the forces are balanced, the resultant force is zero. Okay, Newton's first law, right? You notice that I didn't write F equal ma over here, although you can actually, right? You can write F equal ma and A is equal to 0 because F net is 0. You can do that, but in general, for our syllabus, we will use Newton's first law for balanced forces. Okay? So after that, it's more or less repeated. All right, Newton's second law again. All right, after that, from C to D, okay, he's decelerating with the parachute open. Newton's second law again. All right, and then for D to E, it will be which law? First law again, right? Okay, and finally he lands on the ground.